Okay, let's talk about volume visualization then. Hopefully everybody can get their brains back in the viz. So this lecture has a lot of terminology, and it's kind of building up to something, all these terms. So we talked about ray casting. We talked about these ray functions. We talked about classification, lots of terminology. We talked about transfer functions. And this is where we left off, gradients. Now all this is all background information, and it's leading up to the next algorithm. So we went over 2 algorithms so far. We went over marching squares and marching cubes. So we're building up and we're getting the background information we need to go into the 3rd algorithm. So we need to know the term gradient in order to understand the next algorithm. Gradient, the degree of inclination or rate of ascent or descent, for example, in a highway or a railroad. We're not really talking about highways or railroads. Another definition is an inclined surface, grade, or ramp. From physics, the rate of change with respect to distance of a variable quantity, such as temperature or pressure, in the direction of maximum change, a curve representing such a rate of change. In mathematics, a differential operator that operating upon a function of several variables results in a vector, the coordinates of which are the partial derivatives of the function. So all of those definitions work to some extent. The one that's probably the most helpful today is number 3. We have actually seen an example of a gradient already in this lecture. That is an advanced question. Anybody remember where we might have seen an example of a gradient already in these lectures? That's a difficult question, not easy to answer, I think.
Color scale?
Yeah, you could say the color scale, a color gradient. Yeah, that's an example of a gradient. What's your name again?
Marcel?
Very good, very good. Yes, I wasn't thinking of that, but yes, you could say that's a color gradient. Any other examples? The example I was thinking was the central differences operator from marching cubes. There was a slide describing how to add shading to the triangles, and that uses something called a central differences operator, and that is one way to compute gradients. I don't think the word gradient appeared on that slide, but it is one example. Okay. So these are pictures of gradients, right? These are arrows pointing in the direction of increasing change or increasing magnitude. Same here. These are vectors, right? The mathematical definition derives a vector of which the partial derivatives of the function. So the vectors are pointing in the direction of increasing value, like up the ramp, so to speak. And why are gradients interesting? Because they emphasize transitions. High gradients correspond to high transitions. So that is very important, because areas of data with sharp or high transitions are the most interesting areas because they correspond to boundaries. Like if we shoot a ray into a volume, and we transition from air to skin, there's going to be a very high gradient in the data, and that means we hit a boundary, an interesting boundary, and skin is an interesting boundary. So gradients emphasize transitions or boundaries, and they point to special interesting regions, and they measure changes. And here are some more examples of gradients going from one area to another in this direction and from one set of values to another in this direction. Here the transition is sharper, so the arrow, the vector gradient is larger. That arrow is bigger, it's longer. And here the transition is more gradual, so that the gradient is not as big. The magnitude of the gradient is smaller. That's what those images are trying to show. Now that's leading up to 2D transfer functions. I'll just quickly mention again that this was a 1D transfer function. We had data being mapped to color along the x-axis, and we had data being mapped to opacity along the y-axis. That's called a 1D transfer function because data is mapped to color and data is mapped to opacity. That's a little bit confusing, but that's the terminology. This is a 2D transfer function, which is not trivial to understand. So in the other case, data value was mapped to opacity in that 1D transfer function example. But in this example, opacity is a function of scalar value and local gradient. So we have to understand gradients. These are two pictures of the same thing, by the way, this picture and this picture. This one is drawn in PowerPoint, and this one is taken from the original paper, drawn in the paper. So we have on one axis the scalar value, it's along this axis. And then on the y-axis, or the z-axis, whatever you want to call it, we can call it the z-axis, we have value again, scalar value, but then we have a third axis that is opacity. So we have the scalar value along the x-axis, and as the scalar value increases, the opacity also increases, right? As the gradient magnitude increases, the opacity increases. That's what this part of the pyramid is. So this is like a pyramid shape. And basically what it's trying to convey is that high gradient magnitudes are mapped to high opacity. So it's looking for areas of sharp transition, and those areas are mapped to high opacity. So the greater the gradient magnitude, the higher the opacity. And by the way, opacity is on this axis. You can think of this axis as the same as this axis here. But we've added another axis here to make it a 2D transfer function. So we have scalar value, gradient magnitude, and opacity. And this transfer function highlights transitions or large gradients. That's the point. That's what we're trying to achieve. Can we automatically highlight boundaries or high gradients in the volume data? This picks out a special subset of the volume. So we're automatically, we input a 3D volume, and then we use this transfer function to project a special subset of that 3D volume onto the 2D display. And that special subset is the transition areas, the areas of high gradient magnitude. And by the way, that means we leave out the uniform areas. The uniform areas get transparent. So that's difficult to understand, but I hope that it makes some sense, hopefully. I believe it was maybe a test question last year. And all that terminology builds up to the next algorithm, which is the Rxy Casting Pipeline. And this is an image order method as opposed to an object order method. If anybody has any question, by the way, feel free to interrupt or raise your hand. So you've heard this term ray tracing from computer graphics, and we're not talking about ray casting. I'm sorry, we're not talking about ray tracing, we're talking about ray casting here. They have similarities and they have differences. Ray tracing, so the ray is something they have in common. The image order technique is something that they have in common. But what is ray tracing for? Somebody knew this last time when I asked this. Your name?
Used to simulate the reflections and refractions.
That's right. Your name? So ray tracing is about computer graphics, and it's about computing the lighting and shading of a scene. You want to create some realistic or some fancy lighting and shading of a scene. So you cast a ray into the scene, and that ray samples lighting conditions, right? It intersects with surfaces made of triangles, and then it bounces off those triangles and tries to find light sources, right? So it's actually sampling the scene, the lighting conditions of the scene. And usually the input is a set of triangles or a set of surfaces. That's usually how you represent objects in computer graphics. That's ray tracing. Here, the input is volume data, not surfaces. Surfaces are a set of triangles. Here we're inputting a 3D set of volumetric data on a Cartesian grid. That's the input. And we shoot a ray into the volume, and we're not testing for intersection with triangles anymore. We're testing with intersection with what? Anybody want to take a stab at that? What are we testing for intersection for rather than triangles? Voxels, exactly. Pass that around. So that's a basic summary of the difference. So ray tracing is about radiating objects, surfaces, or slices. In ray casting, there are no objects. There's just a scalar or a density field in 3D. So, yeah. That's the essential difference. It's a conceptual difference, and it's an important conceptual difference, but it's also an implementation difference. Remember this slide? For every pixel, we cast a ray into the volume, and then we sample the volume. Once we hit the edge of the volume, we sample it, and we generate something called an intensity profile, which just is a 2D plot of depth versus scalar value that we encounter along the ray. So it's sampling the 3D volume at every ray and voxel intersection. That's the idea. And we go, for example, from top left to right, and then down. We can rasterize if we want to compute the image. So we compute the value, the color and opacity value of every single pixel on a pixel by pixel basis. That's something that's in common with ray tracing, by the way. Ray tracing is the same idea. Okay, so here's an algorithm to compute a ray casting image. So you might be shocked to see that it's called the Rxy Casting Pipeline, because we love pipelines in this module. I don't know, that's computing. Like, computing is always some processing pipeline, isn't it? So this is what it looks like, and hopefully you can think of the visualization pipeline and the volume visualization pipeline when you look at this and make some comparisons. Like those would be good test questions, for example. So the input is a set of voxel values. Everybody knows what a voxel is here. And then for each voxel value, there's a set of colors that are assigned and a set of opacities. So every voxel is given a color and every voxel is given an opacity, and that's using that transfer, that 2D transfer function we just talked about. And then there's a ray casting / resampling phase to the algorithm, which is the ray, when we shoot the ray into the volume. And then we output a set of colors, sample colors, and sample opacities based on our ray casting or resampling operator. And those are composited into pixel colors. Anybody know what compositing means? Anybody have any idea on that? It means just to add together in this case. So you add a set of sample colors to one another and a set of sample opacities. And the next slides look into each stage in more detail. So this is the overview of the algorithm. You use this in assignment 2, by the way. So you don't have to, the software does it for you. You don't have to implement that algorithm. So step 1 is our 2D transfer function, right? So for every voxel, we compute a set of colors and a set of opacities. So this is computing the colors and opacities. The transfer function we use is the same one we just saw 2 slides ago, right? So we have the scalar values along this axis and the gradient values along this axis. And these are mapped to color and opacity. So this is the new part right here. And as the gradient value goes up, the opacity also increases. And the opacity is not mapped to the scalar values. It's only a function of the gradient magnitude. By the way, that means gradient magnitude, the symbol here. So Phong shading is used to derive the normals. The voxels are classified according to the gradients, and this picks out the transitions or the boundary areas, this transfer function. Because the ones with very low gradient magnitude have no opacity. I hope that can make some sense for everybody. Now, when we sample the data using rays, there are different ways to do that. This is a 2D depiction of that process, by the way. We're not talking about the 2D. It's a 3D process. So this is a 3D array being cast into 3D. We're simplifying the discussion by projecting it down to 2D with this slide. So imagine the ray, this is the view over here. We're sitting over here, or the image is being projected over here, and we cast a ray into the volume from front to back. These are voxels, these squares. And here we are actually trying to compute color and opacity based on a sampling. So we cast the ray into the volume and we sample. This is sampling the volume at regular intervals. In other words, the space between these samples is uniform. right? 'Cause that's a natural approach. That would be like the naive, most obvious natural approach to sample the volume at uniform intervals. Now, if we sample the volume here, it requires interpolation along along this edge, or it could. If we sample the volume here, it might require interpolation along all four of these edges. So 2 interpolations along y and then 2 interpolations along x. So in general, an edge intersection would be 1 linear interpolation, but inside the voxels could be 4 interpolations to derive a value inside those squares. And that's computing, that costs computing time and processing time. Another way of doing it is called scan conversion, and it just uses the data sample at the center of each voxel. So here we're using also called nearest neighbor interpolation. You can think of it as nearest neighbor interpolation if you like. And now the sampling is no longer uniform. The distance between data samples is changing. It's no longer uniform, so it's less accurate, right? So we're taking the sample at the center of this cell, the center of this cell, the center of this cell. But look, then the distance gets bigger here. There's like a jump. And then the center, the center, the center, the center, the center. So there are some jumps. And that results in, anybody know what happens in this case? What the consequences of this kind of a sampling technique are? Can anybody take a guess? It is something we saw already. It is aliasing. Anybody remember aliasing? So that kind of sampling results in aliasing. And you can see it because there's a big jump here. So you can see that it results in aliasing. So this is an accurate sampling technique, but it's very costly in terms of the number of interpolations it requires. This is a very fast technique because it does not require interpolation, but the accuracy drops. And the third one is a kind of compromise. So it samples the volume along edges and voxel edges. So we sample the volume along this edge intersection, which requires 1 linear interpolation, along this edge intersection, which requires 1 linear interpolation, and so on. Here as well, here as well, here as well, and so on. You notice that they're all edge intersections. Interpolating along an edge intersection only requires 2 data samples. So it's fast, but it's non-uniform. But it's still higher accuracy than scan conversion. So it's like a compromise between speed and accuracy. Does that hopefully make some sense to everybody? I hope. So that is the sampling approach. And then we have voxel-based versus cell-based ray traversal. Remember, voxels store their samples at the center, and cells store their values at the corners. So we have, if we use linear interpolation to derive values inside of a cell, it requires trilinear interpolation. Otherwise, bilinear if we're using interpolation along cell edges. So trilinear interpolation is a lot more costly. I don't know if anybody can remember, we had a slide that showed the formula for trilinear interpolation, and I said, oh, you have to memorize that formula for the tests. Anybody remember that? So that's what this is talking about. So that formula is costly in terms of computation time. So we like to avoid it. Trilinear interpolation results in four interpolations along the z direction, then 2 in the y direction, and then 1 in the x direction. So it's 7 interpolations altogether. And maybe I can kind of, I guess that's in a different lecture, isn't it? That cube. Yeah, that cube, that's a different lecture. But anyway, you can go back and look at that formula of trilinear interpolation from a few lectures ago. And this will make more sense, these comments. Okay, and then compositing was one of the stages in the array casting algorithm. If we look that up in the dictionary, it is the sample by sample accumulation of color and opacity values along an array as it traverses volume data. Well, that's not exactly the dictionary, but that's a good definition for this class. And as we do that, by the way, there's a new term here called kernel. 1 or 2 dimensional images that are used for computing the weighted average of pixel images. A kernel is also called a convolution kernel or a convolution filter, just to be as confusing as possible. These 3 terms are used interchangeably in the literature, and it is very confusing. But just be aware, so you have a slide here that's pointing that out. Now, linear interpolation is using 2 samples to compute an average somewhere in between the samples. A kernel is the same idea, but instead of just using 2 samples to compute some sort of average or interpolated value, you can increase that to 2 dimensions and use a whole area, like, for example, 4 data samples or 6 or an arbitrary number. So it's taking the dimensionality and increasing it by 1. So it's a more fancy than linear interpolation. And there are 2 kinds of compositing. One's called back to front, and one's back to front to back rather. So this slide is showing front to back ray traversal. If we consider this to be the front, and we sample the volume from front to back, but it can also be done from back to front. So back to front was the original implementation, but the sort of the next generation implementation was front to back. And this is what the formula looks like. This is the computation of color. That's what the C is, from front to back. This is the opacity. Alpha stands for opacity. So the symbols are here. Delta S is the sample between, the distance between samples, right? I is the sample index. So this is opacity plus color. And here we're computing the opacity, and again, based on opacity and opacity. And actually, I think I have like a demo of this, hopefully, what that looks like. This will be interesting to see if it works. Okay. Okay, something is happening. Okay, that everybody can see that, right? So this is an example of front to back ray casting with one single ray. And the viewer is here, like we are sitting here, and the image that we're looking at is here. This is a line that represents opacity values. So it's opacity values all along this plane, but it's projected down to 2D. And these are color values all along this plane. And this is the object we're looking at, we're trying to look at using ray casting. And we're going to just cast one ray using front to back compositing. So that's the ray. And it's traversing air. So air there are no transitions, it has no gradients. So therefore, its transparency is maximum, or its opacity is minimum. So we have not acquired, we're still on zero opacity because we haven't hit any gradient values. The ray just went forward, by the way. So we're stepping forward into the volume step by step by step. At least I'm trying to have it like that. Now we've encountered a transition or a gradient, an area of high gradient. So we've transitioned from air, for example, to the object. And we sample the color, right? That's our color. And we sample the opacity. Now because that's an area of high gradient, the opacity just went up a lot. So that's a high opacity voxel that we just encountered. We step into the volume further, right? That's still an area of it's still an area that has something that's not just air. So we sample the color again, and we sample the opacity again, and the opacity has increased. Hopefully everybody saw that. Every time we sample the volume and we hit something interesting, we sample the color and we sample the opacity, and it increased. We keep sampling the volume. Everybody see that the ray is going from front to back. Now what's happened is opacity has a maximum value. Its opacity is normalized from 0 to 1. So 0% to 100%. And as soon as opacity hits 100% or 1, we can terminate the ray. Gesundheit. We can terminate the ray because the opacity cannot increase in value anymore. In other words, we cannot see what's behind there anymore. The opaqueness of what we're looking at is at its maximum. So this wall has a maximum opacity, we can't see behind it. But the air in front of us has a minimum opacity, so we can't see past it. So in this front-to-back compositing algorithm, the opacity has reached its maximum. And therefore, we can keep going, but the color doesn't change, right? Even if we keep sampling from front back, even if we keep going in the Z direction. And then we do that for every pixel. So we accumulate color values and opacities for every pixel, right? That's the image order technique. And we end up with a set of color values for every pixel and a set of opacity values for every pixel. And that's just a little demo of like front to back compositing that hopefully makes it more understandable than with just no demo. So front to back compositing can be stopped once the opacity approaches 0. That's called early ray termination. And back to front compositing was the original implementation. So these are some images that are ray casting images. So these images, they look like isosurfaces, in my opinion. Not exactly perhaps like isosurfaces, but these are not generated using matching cubes, for example. They're generated using ray casting. So it's kind of surprising, at least in my mind, it's kind of surprising. It's not very intuitive that you can get these surface structures when you input a set of voxels. Did everybody sign the attendance register? But that's what we're seeing. We're seeing a set of surfaces from voxel data as input data using ray casting. But it's not as surprising if you think that actually what we're looking at on the screen is pixels, and pixels are squares. So when the squares get so small that we can't perceive how small they are, that they can form smooth images. So it's the same thing with voxels. When the voxels get small enough, we can create smooth-looking structures because we cannot perceive necessarily the differences when they get too small. But you can see some artifacts in these images too. There are some aliasing artifacts. Like these lines, you know, those are not natural, right? Those are man-made artifacts. Those don't exist in nature. So that's an aliasing artifact, and there are some other aliasing artifacts, right? So this is a 256 by 256 by 1113 computer tomography data set. Here are some more images with higher resolution and color. Right, this is another ray traced image. And some more examples of different kinds of data. And this is the paper, there's a copy of this paper on Blackboard. So if you saw the lecture and you thought, oh, I didn't understand any of that, you can go and read the paper at your own speed, and hopefully it makes sense. Just one other thing I'll mention about these images. Does anybody remember some of the limitations of the matching cubes algorithm? Anybody remember that discussion? That was on a Monday evening lecture, I think, wasn't it? When everybody was very sleepy. But in these images, the surfaces are no longer necessarily binary. So in the matching cubes algorithm, the surfaces are constructed of triangles, and triangles are infinitely thin. So you're either like on the surface or off the surface. Here, these surfaces have some thickness. They're no longer binary. So there's a transition. Those gradients pick up areas of transition, and it's no longer a binary decision whether or not you're on or off of the surface. And they no longer have to be infinitely thin surfaces. So they can have some thickness. Okay. There's also a book chapter that talks about this in more detail. And are there any questions or comments or anything? Question, what's your name again?
Alex.
Alex.
I was wondering what you call this ray casting.
Yeah.
But I wonder, would it be called ray marching rather than ray casting? Since you kind of use march with the ray. You they'll do it in one step.
Yes, it could be called ray marching. I'm trying to think of.
Because ray casting isn't really volumetric way of rendering things. Because it doesn't have objects still doesn't have volume. It's a tree strand. It's all the voxels as infinite thin surface.
I mean, the marching part of marching cubes. What's nice about the marching part of marching cubes is you can conceptually load in one cube into memory, process it, output the triangles, and then dump the cube or free the memory. In this case, that is not so obvious in the ray casting algorithm. You could load subsets of the volume, maybe not the whole thing. But it would be difficult to march through the volume the same way marching cubes does.
No, I mean there's actually an algorithm called ray marching. That
Okay.
Marches the ray just goes through the scene with small steps, not just one at once. So it knows it can go inside of the volume and see what's inside it. Get at least like that.
You'd have to ask the original authors why they didn't call it ray marching instead of there. Actually, the name of the paper is quite boring. The name of the paper is called Display of Surfaces from Volume Data. So they didn't give it a fancy, the paper title a fancy name.
I think to add to the question, ray casting would be, for example, X-ray, when you actually cast a ray through the volume, and then you sort of accumulate that data. Whereas, at least in here, it's probably like ray marching, because you actually just sample it, like the length of the ray every time. So.
Because ray casting ray terminates once it's surface.
Well, ray tracing, it sounds like you're describing ray tracing a little bit.
Ray casting ray tracing affairs.
I encourage you I made a special tutorial video on the difference between ray tracing and ray casting. Have a look at that. It breaks them down into a table, like what they have in common, what they don't have in common, and how they're different and how they're similar. And I use a nice whiteboard to explain it, which I don't have here. So I think it would help to have a look at that, if you're interested in that subject more. Okay, happy Monday, everybody. See you at 1700 hours.